Today we're going to teach you how to get excellence in physics. Getting excellence in physics can seem really daunting. However, with the right strategies and techniques and a bit of good old-fashioned study, you can really nail down your understanding of the content and start racking up those E8s in your exams. We're going to run you through 2 key strategies that will help you achieve this and illustrate with some examples from Level 2 and Level 3 physics. Feel free to skip around this video using the timestamps so you can get the most out of the video. Before we get started, keep in mind that these strategies are the same in all levels of physics, level 1, 2 and 3. We're also going to be assuming that you're familiar with most of the content from the standards, so if you find you're not understanding some of the words or concepts we discuss, you should check out the StudyTime walkthrough guides to help you alongside this video. Let's get into it. Physics is full of maths, but that doesn't have to complicate things. In fact, we can use the laws and equations to help us gain a much better understanding of the concepts. It's also a really effective way of explaining why particular things happen in a lot of the questions that come up in the physics exams. We can use the following 4 steps to help us with that process. Number 1, identifying what is happening, the context of the situation, and therefore what concept, relationship, or physics law you will be explaining. Number 2, write out the relevant formula or formulas. Number 3, using the concept/relationship identified and the formulas, think about what this means in the context of the question. And finally, number 4, answer the question, explicitly stating the formulas or key relationships or laws. Think about proportionality, incorporating this into your answer. To be able to do this effectively, it's really important to learn the key laws from each standard. We've listed some of these, but for a full list, you should look through the StudyTime walkthrough guides and subject checklists. From there, make sure you understand the relationships that are being described by each equation. For example, F equals ma tells me that if I increase acceleration and keep the mass constant, the force must also increase. These equations are often linked back to the laws shown before as well and help you mathematically visualize what happens when we increase or decrease one value. Once you understand these key relationships and laws, we then want to apply them when we're approached with an explain question. These types of questions are typically asking you to show off your understanding of how changing one variable results in a change in another, or to prove you understand how a particular law applies to a situation. To really show you know what you're talking about, we want to explicitly write these laws or relationships into our answer. Let's look at an example from the Level 2 Mechanics paper. When Sarah lands on the mattress after the jump, the force on her body is quite large. Discuss 2 changes that could be made to the springs of the mattress to make sure Sarah's landing is more comfortable. Explain any physics principles that should be considered to make these changes. Step 1 of our process was to identify what is happening, basically the context of the situation, and therefore what concept, relationship, or physics law you will be explaining. In this case, we are told there is a large force on Sarah's body, which indicates that we want to reduce this force to make her landing more comfortable. We also know we are talking about the concepts related to springs and that Sarah is coming to a stop after falling. This indicates we're thinking about a change in momentum or velocity. This gives us our first part of our answer. Sarah is coming to a complete stop, meaning her momentum becomes 0. Now, if we look at steps 2 and 3, write out the relevant formulas, and using the concept/relationship identified in the formulas, think about what this means in the context of the question. Knowing we're discussing a change in momentum and a force applied, we can look at our formula sheet and see the impulse equation. Delta P equals F delta T. Thinking about what this means in the question, if we want to reduce the force Sarah experiences, we must increase the time the force is applied for. We can't change the total change in momentum as Sarah has to come to a complete stop. You can see this more clearly by rearranging the equation to F equals delta P over delta T. If we increase delta T, F would go down. This shows the relationship between delta P and delta T is inversely proportional. This gives us the next part of our answer. Since delta P must remain the same, the length of time must go up for the force to go down, since they are inversely proportional. Now we can look at step 4 of our process. Our original question was, when Sarah lands on the mattress after the jump, the force on her body is quite large. Discuss 2 changes that could be made to the springs of the mattress to make sure Sarah's landing is more comfortable. Explain any physics principles that should be considered to make these changes. So we need to answer with the two changes that could be made to increase this time and make sure we have explained our physics principles. Thinking specifically about the springs, if we want the process to take longer, the springs must take longer to compress. That means the springs must either be softer, e.g. of a different material, meaning a lower spring constant, or the springs could be longer. In each case, it would take for more time for the springs to fully compress, therefore decreasing the force Sarah experiences. If we add this to our early answers, we get Sarah is coming to a complete stop, meaning her momentum becomes 0. Since delta P must remain the same, the length of time must go up for the force to go down, since they are inversely proportional. To increase the time taken, the springs could either be made to have a lower spring constant by using a different material or made longer. Both of these changes would increase the time taken and therefore reduce the force experienced by Sarah, making her landing more comfortable. And that's it. As you can see, we've identified what is happening in the context, written out the formula, used the relationship between time, impulse and force to work out what must be changed in the springs, and then explicitly stated this relationship when we've answered our question. On a more practical level, we used our understanding of momentum conservation and change to identify the impulse equation, delta P equals F delta T, and then used that to explain how we can decrease the force involved to make Sarah's landing more comfortable. The second part of our answer came from problem solving our way through how we can change the springs to increase T. Finally, we made sure we connected back to the question by saying it would reduce the force experienced, making the landing more comfortable. In our last example, you may have noticed that there is a certain element of problem solving that is needed in physics. The strategy we'll look at now is specifically about problem solving your way through questions. While we're going to look at this in regard to calculation questions, you can follow the same process for questions where you need to explain what might happen as well. When we're presented with a complex question, we want to break it down into smaller parts. To do this, we're again going to follow a stepwise process. Number 1, identifying known and target variables. Number 2, work backwards from the target variable to identify possible equations we can use. Number 3, connecting the variable to a key law or concept. And number 4, identifying other equations to find the unknown variables needed from that last equation. The first part of this process is identifying the target variables, usually the answer, and what other variables we know. Next, we want to take our target variable and identify any equations that have it in them. By using the concept we identified, we can see what ones are most likely. For example, a conservation in energy question will probably use an equation with EP or EK in it, even if we're not given this initially. Some questions can be harder than others, but usually there are clues in the question. Look at what's changing in the question, or perhaps doesn't change when something else does. For example, in a waves paper, if there is a question describing a light wave moving from glass to air, that would indicate we are looking at refraction or changes in wavelength or frequency. Sometimes you'll be given a handy hint where the question says something like, by first calculating this, or by considering this concept. Finally, we can then work out how to find these unknown variables by looking at other equations that have them and putting it all together to get an answer. For example, if we identify P equals mv as the equation to use, but we don't have velocity, we would look for other ways to calculate the velocity. If it was a circular motion question, we might use AC equals v squared over r, if we have the acceleration and the radius. This exact formula depends on the variables and the concept you are looking for, which is why step 3 is so important in helping narrow this down. Now, that sounds complicated, so let's put it into an example adapted from 2018's Level 2 Electricity and Magnetism paper. A metal rod AB of length 0.16 metres is free to slide without friction on 2 parallel metal tracks. The tracks are connected by a conducting wire as shown. The rod AB has a resistance of 20 ohms and the track has a negligible resistance. A uniform magnetic field of strength 1.5 times 10 to the power of 3 Tesla is applied perpendicular to the plane of the circuit. The rod AB is pushed to the left at a constant speed of 3 meters per second. Thus, calculate the size and direction of the induced current, conventional current, flowing through the metal rod when it is moved to the left with a constant speed of 3 meters per second. Our first step is to identify the target variable. The question asks us to calculate the size and direction of the induced current. Therefore, our target variable is current I in amps. Our known variables are the rod length, the speed that the rod moves or its velocity, the magnetic field strength, and the resistance of the rod. We have three possible equations to calculate current. F equals BIL, V equals IR, and P equals IV. Second, the concept we're looking at here is generating current by moving an object through a magnetic field. We have no indication of something happening over time, so that makes P equals IV unlikely. F equals BIL looks promising, but there's nothing really about something moving through a magnetic field, rather about a force applied due to a magnetic field. V equals IR doesn't seem to be relevant, but we have R already, and so we can look at step 4 of our process to see if this formula may work in this context. Step 4 was identifying other equations to find the unknown variables needed from that equation. So we are looking for a formula that has voltage in it. And from step 3, we know that it should be related to moving magnetic fields. From this, we can identify V equals BVL. If we check this against our known variables, the magnetic field strength, the length of the rod, and the velocity of the rod, we can now calculate the voltage. So from this problem-solving approach and working backwards, we know our first step is to calculate the voltage. So V equals BVL, which then translates to 1.5 times 10 to the power of negative 3 times 3 times 0.16, and that gives us 7.2 times 10 to the power of negative 4 volts. Then we use that to calculate the current. So V equals IR, we rearrange that so it is I equals V over R. We then get 7.2 times 10 to the power of negative 4 divided by 20, and we are left with our current equaling 3.6 times 10 to the power of negative 5 amps. Now we've calculated the size of the current. However, if we check back at the question again, it asks us to calculate both the size and direction. While this part isn't needed to demonstrate the strategy we're practicing, in this case we use the right-hand slap rule to recognise the current will be in a downwards direction. Our final strategy is more of a quick set of reminders for your exams. Often small overlooked mistakes can be the difference between a merit or excellence and really limit your mark. Here's 3 things you should always make sure you're doing to avoid this happening to you. 1. Convert your units correctly and make sure you have them in your final answer. 2. Answer with the correct number of significant figures. And 3. Explicitly state the relationships and assumptions. For example, because energy is conserved. We took a look at a couple of different examples from Level 2 Mechanics and Electromagnetism, but let's take a look now at how these strategies apply to some Level 3 examples. First of all, a mechanics question from 2016. The following diagram shows part of a roller coaster track with the car at 2 positions. At the top of the circular loop, the force that the track exerts on the car is 0. Using energy considerations, calculate the height h of the hill if the radius of the loop is 5 meters. You may assume that friction is negligible. Let's remind ourselves of our process for complicated calculation questions. Number 1, identifying known and target variables. 2, work backwards from the target variable to identify possible equations. 3, connecting the variable to a key law or concept. And 4, identifying other equations to find the unknown variables needed from that equation. Our target variable here is the height of the hill. Our known variables are the radius of the loop and the acceleration due to gravity. Looking at step 2, the only equation we have with height as a variable is EP equals mgh, though height could also be a length or a distance, giving us the following as our overall options. EP equals mg delta h, W equals fd, and V equals delta d over delta t. Now, looking at step 3, the question tells us to use energy considerations. This already suggests conservation of energy is the concept we will be looking at, highlighting MP equals mg delta h as the best equation to proceed with. Our energy at the top of the loop must be the same as the energy at the top of the hill. So we just need to work out what energy the car will have at the top of the loop. The car will both have a potential energy, since it is not at ground level, and kinetic energy, since it is moving. By adding these together, we can get the total energy of the car. E total equals EP plus EK, half mv squared plus mgh. We also know that all of the energy must have come from the potential energy in position A, so we know that E total, mgh, where h is the height at position A. This gives us mg capital H equals half mv squared plus mgh. It is going to start getting confusing with two h's in here now, so let's simplify it a little bit. We know that the height of the loop is 2 times the radius, so we'll substitute 2r in for the height of the car. mgh equals half mv squared plus mg2r. Simplifying down to mgh equals half mv squared 2mgr. Let's take a breather and recap quickly. Our target variable here is the height h, and we have the radius and we know the gravitational acceleration g. While we don't know the mass, this can be divided out of every term. This leaves velocity as our only unknown left. Going back to step 3 of our process, we know we're looking at a vertical loop, which logically correlates to a vertical circular motion. From this, we know that the force at the top to be 0. That means the centripetal force applied must be equal to the gravitational force on the car. Fg equals Fc, therefore mg equals mv squared over r. This formula only uses the mass, gravitational acceleration, and the radius. And the mass can be divided out as well. This gives us an equation that aligns with step 4 of our process. So if we rearrange this for v squared, we get mg equals mv squared over r, changing that to g equals v squared over r, gr equals v squared. We then substitute that into our big, long conservation of energy equation. mgh equals half mgr plus 2mgr. We now have an equation we can solve. We'll divide everything by mg to get h equals half r plus 2r, therefore h equals 2.5r. And finally, to put in our value for the radius of 5, h equals 2.5 times 5, h equals 12.5 meters. Next, let's take a look at a question from a past waves exam. Susan knows that as the car accelerates, the frequency of the sound produced by the engine increases. After the car has passed Susan, it accelerates away with an increase of engine frequency of 10%. When the car's speed has increased by 10%, will the frequency Susan hears be higher due to the higher revs or lower due to the Doppler effect? Justify your answer using equations or simple calculations. Since this question asks us to justify, we're going to be using our first strategy. Step 1 is therefore to identify what is happening, the context of the situation, and therefore what concept, relationship, or physics law you will be explaining. In this context, we're already told we are thinking about sound frequency and the Doppler effect. Specifically, we're trying to work out whether the increase in frequency due to the engine will be greater than the decrease in frequency due to the Doppler effect. Step 2 of our process says to write down the relevant formula. In this case, the only relevant formula is the Doppler equation. The apparent frequency equals the actual frequency times the speed of sound divided by the speed of sound plus or minus the speed of the source. Now, using step 3, we want to think about how this formula relates to our question. So let's think about the proportionalities and the context here. The apparent frequency is directly proportional to the frequency. The apparent frequency is inversely proportional to the wave velocity plus the velocity of the source. Let's take a slightly closer look at these relationships. Since apparent frequency is proportional to actual frequency, if the actual frequency increases by 10%, the apparent frequency also increases by 10%. Since the apparent frequency is proportional to 1 over the speed of sound plus the speed of the source, if the speed of the source increases by 10%, this will be less than 10% of the total denominator since the speed of sound remains unchanged. This means that the decrease in apparent frequency will be significantly less than 10% as well. Now, we can use that to answer our question, explicitly stating the equation and the relationships. The Doppler equation, apparent frequency equals actual frequency times the speed of sound divided by the speed of sound plus the speed of the source, shows that the apparent frequency is directly proportional to the frequency and inversely proportional to the velocity of the source added to the velocity of the wave, or the speed of sound. This means that if actual frequency increases by 10%, the apparent frequency increases by 10% as well. However, if the speed of the source increases by 10%, the apparent frequency will decrease by less than 10%, as it is not a 10% increase to the overall inverse relationship, the inverse relationship being the speed of sound plus the speed of the source. This means that the apparent frequency will be higher than the original frequency, as 10% increase from the engine frequency is greater than the decrease due to the Doppler effect. So now you have some solid strategies to help you answer physics questions all the way up to excellence. These strategies aren't a replacement for study, but they are a way to maximise the results you get from the work you put in. Your next steps are to make sure you practice applying these by doing loads of practice questions, and also that you have a solid foundation of knowledge. By combining these strategies with a good knowledge base and plenty of practice, you'll have a really strong pathway to excellence for your physics exam. All the best and good luck!